This is lecture 19. So in the previous lecture, we saw another way of designing a common source amplifier where the MOSFET was biased using a constant current source. However, the current source was attached to the source, right, instead of the drain, right. So if I have to sketch the same circuit again, so this is what we saw. We saw a couple of things. Number one, this way of biasing does not need anything, in the sense that you stick in the current source at the source, and given that you have some appropriate bias voltage at the gate, the transistor biases itself, right. And then we had to apply an input, we had to AC couple the input. That's what we did. And however, we saw that in this case we had to ensure that in a common source amplifier the source has to be incrementally grounded. The way we could do that was by connecting a capacitor, right? Connecting a capacitor C2, and we assume that C2 is of infinite value. And how was the load connected? The load was again connected through another capacitor C3, and this is what our network was. Okay, so this is where we stopped. We did the analysis of the small signal model and we stopped here. But like before, we like to know what is this infinite capacitor, right? What is the value of this infinite capacitor? Because ultimately at the end of the day nothing is infinity. So we need to understand what is the minimum value of capacitance that we can get away with. Okay, so what is the principle of finding out the minimum value of the capacitance? So principle is, for a first order circuit, so for finding mean C so that it acts as a short circuit at a frequency omega naught radian per second, we need to find the time constant, right, if the network is first order. So this is important. So the network has to be first order. If the network is not of first order, the time constant is of no use, because you cannot define a time constant if the network is not of first order, right? Okay, so which means that I need to figure out what the time constant associated with C2 is, right? So in order to figure out the what is the time constant that is associated with C2, what should we do? Let me mark the transistor M1. So obviously we have to first linearize the circuit, right? Replace the MOSFET with a small signal equivalent and then do the analysis, right? So let's do that. So what should we do? So if we notice, what should I replace the MOSFET with? The MOSFET is replaced with a small signal equivalent, right? So this is GM-VGS. Okay, what is source? What is the source of the MOSFET? Note that the current source I0 goes to infinity in the incremental model. So I am left with only C2, right? So I am not replacing C2 with an short circuit because we are trying to figure out the time constant associated with C2. So I am keeping the C2 as is, right? So I am keeping C2 Okay, so this is Vs, this is Vg. What is associated with Vg? With Vg, I have a parallel combination of R1, R2 to ground, right? So parallel combination of R1, R2 to ground. What else do we have? We have C1, right? We have C1. What else do we have? We have Rs, and then we have Vi, right? We have Rs and we have Vi, but in order to figure out time constant, we don't need the input. We can de-energize the input. Setting Vi to 0 is equivalent to shorting this terminal. Okay, so far so good. What is happening at the drain side? At the drain side, I have a resistance to VDD, which means incrementally resistance to ground, and I have a C3 and RL also connected, right, in parallel to it. So what do we have here? We have R3, this is also to ground. I have C3 and RL, which is also to ground. So what I'll do, I'll just make all the grounds same so that there is no confusion. So these are all the grounds are tied together, right? So all the grounds are tied together so that there is no confusion. And what we need, we are trying to figure out what is the time constant associated with C2. Okay. Okay. So you might say that this is not a first order circuit. You would be right. This is not a first order circuit because you have three capacitors C1, C2, C3. But let's see whether this is something can we get more intuition because of the circuit is of a certain type, right? So what do you think will be this voltage Vg? So note that this loop is a self-contained loop and it doesn't have any source associated with it, right? So no current will flow into the loop, right? Since no current will flow into the loop, what do you think will be, and this, given that this is 0 volt, what do you think the voltage at Vg will be? Incremental voltage at Vg is 0, right? So Vg goes to 0. Okay, so what is now, if Vg goes to 0, what is Gm times Vgs? Gm times Vgs becomes Gm times Vg minus Vs, which is Gm times minus Vs, right? So I can replace this with Gm times minus Vs. Okay, great. So if we have to figure out the time constant associated with the capacitor C2, right, then what should we do? We need to find out the Thevenin equivalent resistance looking from the two terminals of the capacitor, right? So essentially we need to find out the Thevenin equivalent resistance looking into this, right? We can remove C2 and find out the Thevenin equivalent, right? So let's do that. So in this case, now I can basically remove the loop at the input end because that is 0, that is of no use. So let's remove that. So what am I left with? The circuit becomes significantly simpler. So the input side Vg becomes grounded. Okay, so this becomes Vs. Right. Let me draw it in a different page so that would be clearer. So Vg is grounded. This is Gm times minus Vs. and I have the capacitor here. So I am trying to find out the impedance looking into the network from the two ends of the capacitor. So I don't need the capacitor, I can put a test voltage, right? So I can put a test voltage V test, and I want to figure out what the I test is, right? Okay, what is connected at the other end of the drain? At the other end of the drain, I have a resistance connected to ground, and I have a combination of capacitance and resistance connected to ground. Okay, fine. Okay, so far so good. So now you notice that here we have the current source GM times minus Vs pointing downwards. Negative is something that is we are not particularly good at handling, at least for the intuition purposes. What I'll do is I will make it GM times Vs and I'll flip the direction of the current. Okay, so let's do that. So I'll flip the direction of the current, and I will make this. So let me flip the direction of the current source. I make this GM times Vs. Okay, this is Vs. Okay, so what is Vs in this? Vs is equal to V test, right? Simply because I have connected V test between Vs and ground, right? So what is GM times Vs? So GM times Vs becomes GM times V test. Okay, and this happens to be the current I test, right? So what is V test over I test then? So let me write it here. So then V test over I test becomes 1 over GM the transistor M1, right? And this becomes equal to the Thevenin resistance associated with the capacitor. Now note that 1 over GM is purely resistive, right? It doesn't have any imaginary term, any S term, which essentially means that now if I have to draw the equivalent circuit from the capacitor C2, from the perspective of the capacitor C2, what do I see? I see capacitor C2, and what do I see on this side? What I'm essentially asking is, what am I seeing this side? I am seeing RTH. What is RTH? RTH is 1 over GM. So what do I see here? I see 1 over, right? So now if this is what type of circuit, what is the order of this circuit? Obviously this order of the circuit is a first order, so we can associate a time constant. What is the time constant associated with the capacitor C2? Let's call it tau 2, that is 1 over GM times C2. And in order for the capacitor to behave like a short circuit, what needs to happen? This has to be much greater than 1 over the frequency of interest at radian per second, right? Omega naught is radian per second, which means that C2 has to be much greater than GM over omega naught, right? So if you can ensure this, right, then C2 will behave like a short circuit at omega, right? Okay. What about then? Let's turn our focus to the capacitor C3, right? So again, for C3, the input side of the network, the input loop doesn't matter, because while we are calculating time constant, the input side is essentially not there, right? Because I don't have any input, uh, and there is also no connection between the input and the output, right? I mean directly. So I can essentially remove this. Okay. What about, what should I do now? So like before, I have to find out the time constant associated with C3, which effectively means that I have to find out the Thevenin equivalent impedance looking from these terminals, right? So what should I do? I should put again a test voltage source, V test. I need to find out what I test is, right? Okay. So what do you think in this case? Uh, what will be the effect of this GM times Vs? Right? So essentially what I'm asking is, how much of the ITS do you think will flow into R3, and how much of it will uh, flow into the network in the bottom, right? So what do you think will happen? So let's assume that some part flows and it generates a voltage Vs, right? Okay. So what happens then? So if some part flows down, right? So if some part flows down and it generates a voltage Vs. So if I find out the KCL at that node Vs, what do I get? I get the amount of current flowing down. So KCL at Vs leads to minus Gm times Vs, which is the current flowing down. It should be equal to the current flowing down from the capacitor, through the capacitor. And what is the current flowing down through the capacitor? This is SC2 times Vs, right? This should be SC2 times Vs, right? If you are not comfortable with SC2, let's call it J omega naught C2 times Vs, because we are talking about some frequency omega naught, right? We are trying to figure out. So which means it becomes Vs Gm plus J omega naught C2 is equal to 0, right? Which means what? The only possible solution which can be generalized is Vs has to be equal to 0. If Vs is equal to 0, what does it imply? It implies that there is no current flowing downwards, right? So there is no current flowing downwards. Then what does it imply? It implies that the only loop uh, that is in existence is the loop on top. And what is the equivalent resistance? What is the equivalent Thevenin resistance look in the loop on the top? It is R3 plus RL. So that's right. So RTH in this case is R3 plus RL, which essentially means that the tau associated, the time constant associated uh, with the capacitor at C3, or the capacitor C3, is C3 times R3 plus RL, and this has to be much greater than 1 over omega naught, which means C3 has to be much greater than R3 plus RL times omega naught, right? Note that this hasn't changed, and this constant hasn't changed from the original common source amplifier that we initially envisaged. However, the important addition here is that we have a additional uh, constraint, because we have an additional capacitor C2. Okay. Okay.